Yesterday, we had done the demonstration where we had eventually gotten to the point that mentioning that water itself is a polar covalent molecule, meaning that has a positive and negative side to it, right? And so when we place then that pure water into a beaker and then introduce into that beaker an ionic compound and then a covalent compound that's non-polar covalent like sugar, we found that when we place the electrodes of the light into the saltwater solution, the light shines. When we put it into the sugar water, it doesn't do anything. And it has everything to do with the fact that the water molecule is actually able to get in there and interrupt. Oops, how about I change the screen over? Get in there and interrupt the ionic compound. Right. So if we consider that we have NaCl, we know it's ionic. Why? What tells us about this compound right away that's ionic? Yeah. Metals and nonmetals. So we know that we have a positive component and a negative component to it. So the water, the oxygen side of that water molecule is going to set itself up to surround the sodium. Maybe change this into a cloner here. There we go. Oops, I want to do an infinite cloner. There we go. All right, so this guy will set itself up and surround the sodium portion of this. Oops. Work with me here. There we go. Like so. Let's turn this guy off. There. All right, so these water molecules are going to sit there and surround this sodium cation and separate it from the chlorine. And so that's how this is going to get in there. Not only to break down and dissolve the crystal of salt, but also get in there and dissociate the actual compound sodium chloride. And when it does that, that's what allows then the current to flow through the solution. Because now you have these free-floating positive and negative charges hanging out in here. If we can get all of NaCl, let's group together. Darn it. The Cl component, this chloride component, can float and move along and help move charged those electrons from one electrode to the next. So the light lights up. If we consider what sugar is, right, being C12H22O11, right, this entire molecule, we made mention that it's non-polar covalent. So why can't water break this molecule up? But it's able to do so with sodium chloride. Okay, it's not ionic, well, of course it's not ionic because it's all nonmetals, but it's a non-polar covalent compound, which means what about the molecule overall? No. Well, ionic bonds are stronger than covalent, but you're getting close. What is water? How is water able to interact with the ionic compound? Because the ionic compound has cations and anions. It has a positive charge and a negative charge. Does this nonpolar covalent molecule have a positive and negative side to it? No. It's going to be overall spread out very evenly in terms of the electrons that are being moved and shared in this molecule. So the only thing water can do is actually get in between. Get in between another one of these guys. Another one of, did we clone this? There we go, perfect. Like another one of these sucrose molecules. So water can get in between and dissolve sugar, but it can't get in, it can't break the molecule up. So therefore, in solution, you have a polar molecule like water, the solvent, but your solute, this sugar molecule, is still stuck together. It's still a complete molecule in water, right? So, and that's different than when we have NaCl in there, right? So that's why we see the light up when we are in salt water versus sugar water, right? And then now if we go back to our original kind of probing question, why when water is cooled to the point where it freezes into solid ice, why does it expand, right? Why does ice float on liquid water? So if these water molecules have a positive and negative end to them, right? We've mentioned that the oxygen side is going to be a partial negative charge. By the hydrogen, it's going to be a partial positive charge. How will these molecules want to hang out as they get slower and slower and slower? What will we want to be near what? If you have more than one water molecule, how will they want to be hanging out together? Is there going to... Yes, go ahead. Yeah, it doesn't necessarily need to be near two of them, but it needs to be at least near one of them that's more positively charged. You're right. And so it's kind of already set up in that way where, it would not want to be hanging out like this. Like that would not want to happen. It's going to want to be where the hydrogen is near the oxygen, another hydrogen is near an oxygen, a negatively charged guy. Same thing here, hydrogen next to oxygen, hydrogen next to oxygen, hydrogen next to oxygen. It's going to want to hang out that way. And as they get slower and slower and slower, what happens when things go into solid state? What's going to happen with their molecules? Are they freely moving, or what happens to them? Yeah. They're going to be kind of locked in their position, and they kind of vibrate in place because they have some temperature, right? They're not absolute zero, like 0 degrees Kelvin, or negative 273.15 degrees Celsius, right? It's like at the freezing point of water, 0 degrees Celsius. Right, so they're going to get locked into this location. Now, if this is liquid water, we have like water molecules kind of floating in through here and flowing across there, and they kind of hang out and maybe rotate and kind of like all like just moving around and flowing. But when we actually get into, let me put this guy back. When we look at how like water would set itself up when it forms into a solid state, it gets kind of organized. And we notice that, look, there's a spot, there's a location like in this matrix of water where other water molecules aren't going to be found. And so what happens? If I have the same number of water molecules and I bring them to a solid state, if I freeze them into ice, right, what's going to happen to the amount of space they take up? If now all of a sudden there are actual like gaps between all the water molecules where molecules can't be anymore. What's going to happen to the overall volume or space that water takes up? Let me remove the circle of no molecule land. Okay, and let's say same number of molecules out here, right? And I say, you know what? They're flowing around one another and everything else. Do they take up more or less space now? They take up less space right now. Say this is liquid water. Okay, when we start to slow them down, when they can no longer be wherever they want to be, they actually have to line up hydrogens near oxygens. They can't just flow and spin by each other, right? We see them start to set up like this. Oops, there we go. And now we have a space where we can no longer have, any water molecules in. Does this take up more or less space now? More space, and now it's solid. So does the volume increase or decrease? It increases when you freeze it. So what happens to the density of a material if you have the same amount of stuff, the same mass, the same number of molecules, yet they take up more space? What's going to happen to density? Right? D equals m over v. If v gets bigger, the resulting calculation becomes smaller. So density will decrease. It's like if you want to think about it, like water's normal density. Well, liquid water's density is 1 gram per milliliter, or 1 gram of mass per cubic centimeter of space. Right, 1 over 1. If we freeze water, it's going to take up more volume. So it's going to be 1 over a larger number, like maybe 1 over 2 or whatever. That's kind of extreme, but you get the idea. So it should be a smaller dense. It's going to be less dense. So if you put a less dense object in more dense liquid water, it's going to float. It's going to float. So now this is the backstory. This is why when we chuck solid ice, solid water into liquid water, it floats. It has everything to do with understanding how the molecule works. You had to get there to explain everything. I mean, the easy answer is, like we see in all physical science, if the density is less than what you have it in, it's going to float. in that solution or in that medium. That's absolutely correct. But then we have to go, if we want to explain why, they're both the same compound, right? It's liquid water and solid water. It's water, water, water. So why does it seem to be, why does it expand when we freeze it, when we bring it to a solid state? When everything else we seem to be aware of, like copper and iron and everything else, that stuff shrinks when you bring it to cooler temperatures, right? Water does the opposite. And this is crucial. This is crucial to life, because think about like a lake or a pond or a stream, right? If water, when it got solid, would become more packed and dense, well, it wouldn't float. It would sink to the bottom of the water, right? So if you think about Lake Erie over the winter, not this past winter because it's pretty mild, but a winter where it actually freezes over rather completely, right? Since ice floats, as water turns solid, it rises to the top. You have a layer of pure water frozen on top of that lake now, and then there's still liquid water below that. And that's what allows life to survive through the wintertime. If it was the other way around, if ice would sink, then your ponds and lakes and stuff would freeze from the bottom up, but they'd freeze solid all the way through. Right? So that's what allows life really to survive in cool conditions seasonally, is the fact that it does this. Okay, so that's all good stuff, man. That's all good stuff. Okay, so if we hop back over to moving in and trying to complete some of these notes here, our last stop before we actually get back into the main outline, which is like the very first page of the handout, is diagramming covalent things. Right, we've done a Lewis diagram of how ionic compounds form, right? Using Lewis dot diagrams for the elements, using arrow to show the transfer. So we've done that. But we also should be able to do the same thing with covalent things in a very simplistic way. Right? So this is the last thing. If you have a little bit of room left, we're going to try to squeak this idea in here. There we go. We just need a fresh page to work out of. Okay, so ionic compounds, and again, we can go back with NaCl. We would sketch out that sodium has one valence, right? So this would be the Lewis dot for sodium. Chlorine has how many valence?
7.
7 altogether. So 1, 2, 3, 4, 5, 6, and 7. Okay, notice that I decided to put my unpaired electron closest to sodium because I'm going to show you that it does something bonding-wise. Right? And we know that this is a metal and a non-metal. So the non-metal is going to want that electron like super bad. So we showed that transfer, that taking over the electron and going over to chlorine. Right? So we're okay with that. We agree to this process. Okay, so chlorine's going to take this electron away. All right, I'm going to try to group all this together, and we're going to, because I'm going to shrink it a little bit and move to the side. All right, so to kind of finish the whole process out, I'm going to draw like kind of a big fat arrow just to differentiate between what I showed in my red arrow. All right, so there we go. It's kind of a nice crappy arrow. And now what happens? Now with the electron moved, sodium becomes what?
NaCl.
It will eventually, but what is it when the electron gets moved away from it?
Just Na.
Oh, with what?
A complete outer shell.
It does, but what about sodium has changed?
Positive charge.
It's positive charge. So Na plus, and we're going to combine that with chlorine, which is now negatively charged. And the result from this is, now case,
NaCl.
NaCl. Yep. All right, so that's pretty simplistic, right? You can sketch this out. This is something that you should feel confident in doing. Given like some basic elements on the table, you should be able to kind of figure this out. You should be able to walk your way through it. If you can dot them, then you can figure out the rest. Right? If we were to consider like electronegative values, I think sodium's like 0.98 or something, and chlorine's like 3.16. So this change in electronegativity is the difference between the two. And I don't know.
2.14. No.
No. 2.18?
Yeah.
Yeah, that sounds right. Alright, that's a big difference. That means that this number, this big difference would say that this is going to be ionic all day long because of how different they are. That chlorine is so greedy for them, it's going to take it and not give it back. Right? We should be able to kind of interpret that. Now, if you do not grasp the trend in electronegativity values, you can always go online and use a ptable.com and look up the electronegativity values if you need a chart to help you, right? But let's then consider like on our note page that I just kind of took down, we're going to consider 3 different molecules, 3 different covalent compounds: oxygen, so O2, methane, which is CH4, and then also carbon dioxide, CO2. We're going to look at those 3 for examples of how we would diagram those out. Okay, first, oxygen, very easy. It's O2, but we're going to be dealing with 2 oxygens. So we're going to go ahead and do our 1, 2, 3, 4. How many dots does oxygen get?
6.
6 dots. It has 6 valence electrons. It's in group 16. We agree?
Yes.
All right, I know you agree, but I want to make sure that everyone's also on the same page. Okay. All right. So I'll go ahead and just dot it up as normal. You might find that you would choose to do it differently because I'm going to make a mess here in a moment. And then we'll do the same thing with this guy. 1, 2, 3, 4, 5, and 6. Right, if you do like the up, down, left, right as you dot them, you can kind of make sure that you pair them up as appropriate. Okay, so I have my 2 oxygen atoms, and if I consider what they are, they're both nonmetals, so they're both wanting electrons. So they're going to do what with them? Are they going to take them or share? Share. They're both going to want electrons, so they're going to try to work things out, work things together. All right, so I'm going to draw a circle around the unpaired electrons. Right, these guys are unpaired on each of the oxygens, and they're going to get shared between the 2 of them. And then also, make a smiley face here. Those guys will get shared. We agree. This would make both of them happy, right? If both of them got shared back to the right side of oxygen, he'd have an octet, 8 electrons around it. If they got shared back the other direction, the other oxygen would also be happy with an octet. This works. Okay. All right, so now I'm going to clean up the sketch a little bit. All right, so I'm going to say, all right, this is going to result in this idea where I'm going to have an oxygen, and it's going to have 2 bonds. One shared pair, the second shared pair to the other oxygen. And then I also have to make note that there are some electrons on this, here and here and here and here, that were not part of the sharing. So they stay with their respective oxygen. So I'm going to show those dots as well. So here we go. Our 1, 2, and 3, and 4 dots on this guy. Our 1, 2, 3, and 4 dots on the other one. So that would be it. That would be showing the final product of these guys hanging out and forming a molecule of oxygen gas. Right, the last thing we might be asked to mention or figure out is this bond here, is this molecule polar or nonpolar? So we have to look at the bond. We have to consider, is that nonpolar covalent or polar covalent? How do we figure that out? Yes, sir. We would know that, though, by having to do this step next. What's the next step to figure out what type of bond this is? I mean, we know generically nonmetals with nonmetals are covalent compounds. We know that. But we know that as far as covalent compounds are concerned, there can be polar and nonpolar. So how do we know that whether it's polar or nonpolar? How do we figure that out? What do we need to know? What do we need to compare? What do we need to compare between the 2 oxygen atoms? Yes, Corinna, right?
Yeah. Isn't that their electronegativity?
Check their electronegativity. Yeah, compare those values. And you're right. It's the same atom, Mr. Cohen. It's oxygen and oxygen. It's the same element. They're got the same value. You're right. And if you can cut to the chase on that, that's great. But if not, then we just look them up, right? Oxygen's like 3.44, and this guy is 3.44. And the difference, the change in the En value, is the difference between these two. So it minus itself is going to end up with 0. Yeah. So this tells me if the En is rather low in number, like usually like 0.5 or less, then it's going to be what? If there's not much difference between their greediness for electrons, if they desire them both the same, they're going to share very They both have the same desire for electrons. They're going to share very equally. Yeah, yep, you got it. Very equally. So this is going to be what? Polar or nonpolar? Nonpolar. Yeah, this is going to be nonpolar covalent all day long. Yep. Even Stevens. Perfect. Are we okay with this process to kind of work through oxygen? All right, let's try another example then.
How do you evaluate the polar and non-polar?
Just like we did, we check EN values and see how different they are.
Like, how do you know if it's polar? Oh, is it like the numbers? Like,
yeah, this would come from a periodic table. Like we would go to, I think I might have it pulled up. Like if you go to ptable.com, all right, can I just do, let's see if I can get back to the normal one. Right, when you first go to like p-table, it's going to show you a periodic table like this, like the ordinary one. But we want to know some properties, so we click on the property tab, and then we click on electronegativity as one of our choices, and it's going to give you the numbers. Like it shows you the number for oxygen being 3.44, or carbon being 2.55. It's that scale of 0 to 4, right? And we write them down. Oxygen is 3.44, so both of them were oxygen. So we look at how different they are. We subtract them from one another. The lower the number, the less polar it is.
and if it's like below 2,
If it's like 0.5 or less, we're going to say that it's going to be non-polar covalent. If it's between like 0.51 to I think it's like 1.7 or so, it's going to be polar covalent. If it's anything beyond that, it's ionic. They're so different that the greedy one doesn't give it back. It's a spectrum. And this might be where things have been a little bit different in terms of like what you've been told. Sometimes we don't tell you the whole story right away because it's complicated. There's a lot more stuff going on. The bigger the atom, the more stuff you got to consider. But at the end of the day, just like the rate, like the visible light spectrum, like we know that it's not just Roy G. Biv, right? There's like a bajillion trillion different hues and of color, from the reddest of the red to the purple of the purples. Right? We know there's a large range and spectrum of different colors. Same thing here with bonding. There's a range of situations, right? Ranging from even Steven sharing to I'm not giving that guy back ever, and stuff in between. This is and so we'll come across I think in this next one somewhere in between. So let's do CH4 and see how that plays out for us. All right. So what I want to do is I want to sketch in the Lewis dot for each element. So I'm going to put carbon in first because it has 1, 2, 3, 4 valence. And if I'm going to put it with 4 hydrogens, right, I'm going to put the dot nearest the carbon because I think we know how this is going to play out. Right? Carbon has 4 unpaired electrons. Hydrogen has 1 unpaired electron in its valence. And we know that hydrogen only needs 2 electrons total to be complete chemically. So it just needs 1 bond, right? And then hydrogen's satisfied, right? So we sketch these out like that. We're going to show that these 2 will be shared. These 2 will get paired up. These 2 will get paired up, and these 2 will get paired up. All right, that's pretty simple. That means then this is going to result in a structure or a molecule that has carbon at the center, and we have a single bond to each of the hydrogens. And I'm going to go ahead and while you guys are kind of following along here, I'm going to go ahead and group this, and that way I can kind of shrink this guy and move him over. And we'll grab this guy as well and move him over. There we go. Perfect. Okay, so now the big question: is this molecule, is it polar or nonpolar? Well, we got to look at the bonds. So are these bonds here? Oh, well, would this be ionic? No, because we're showing shared electrons. So no way is it ionic in any stretch of the imagination. So we can rule that out right away. But now we got to consider like whether it's nonpolar or polar covalent with the bonding, right? So if we look these guys up, right, we would note that hydrogen is 2.20, and that's for all of them, and carbon is 3.44. Yeah. Wait.
Yeah. No.
No.
Oxygen.
That's for oxygen. This is
3.55.
2.5. Thank you. Sorry, it's been a day of numbers, that's for sure. All right, so 2.55. It shouldn't be much different, which is good. Okay, that makes sense. So now we determine like how different they are. So what's the delta En, or what's the change in electronegativity or difference?
0.35.
Right, it's going to be 0.35 different. Right, so our change in electronegativity is equal to 0.35. Right, we'll kind of just box that guy in, and that's for each of these bonds. It's like that. So, what type of bond is that? Is that nonpolar covalent or polar covalent? Nonpolar covalent. So, if that's the case for all these guys, this whole thing is going to be nonpolar covalent. It's going to be a nonpolar molecule. It will not have a defined positive or negative region around it. It will not be. It's probably not going to be able to be dissolved by water because it's not polar. Now, if you're the type of person that looks at these numbers and says, but these are different, they're not the same. Okay, you're right. Carbon slightly desires electrons just a little bit more than hydrogen, but it's not big enough of a difference to permanently or hog them away for any notable effect, as far as we're concerned. So this falls in that range of nonpolar covalent, and that should be satisfactory for now. Okay, so are we okay with this guy?
Yes.
All right. So the last one, then, carbon dioxide, CO2. CO2. Sid, how about you do this for us? It's all you. You got it. We want to see the Lewis dot for each element, and then we want circles showing which electrons will be shared, and then write the proper lines representing the shared pairs of electrons.
So it'll be like this one, right?
Okay. Yep. So far, so good.
And then I can't remember what that one is.
It's in group 14, so how many valence does it have? Remember, the ones position tells you how many valence. Right? So in group 14, it has.
Wait. So it'll be
No. Hit the undo, hit the back, the little undo arrow to the left-hand side.
so.
Yeah, this is the curvy one. One more. Okay. Now remember, when you put dots around them, do north, south, east, west, or up, down, left, right when you put your dots in. So there's your first one at the top, second one at the bottom, third one, right, and then the other one left. There you go.
Oh, okay.
Right. Yeah, each quadrant needs one electron first before we can double them up. Okay. Now you need another oxygen because it's O2.
Oh.
It's CO2.
Should I put on this?
Sure, you'll like it if you do that. It'll make drawing a lot easier for you.
And then what are these ones like?
Yeah, can you switch the color though? Can you circle the ones that will be shared? Use go back to your pen, switch it to blue or something.
Can I do green?
Sure.
Okay, and then
Circle the ones that belong together. All right, sure.
then these ones.
Okay.
And these ones.
Whoa, Nelly. All right, they're not. They're probably not going to get shared oxygen to oxygen. A molecule won't necessarily form a triangle. All right. So, what carbon kind of has a couple unpaired ones left.
Mm-hmm. These two.
Right. So those need friends too.
So with these ones.
Yeah. Sure.
Well, how else would you
That's
do
fine.
that?
That's fine.
Okay.
I just draw it around it, but that's fine. Oh no, you can't. One electron.
Oh, yeah. Sorry.
Yes.
We go to the bottom.
Sure.
that?
There we go. Okay, now now we want to clean up what we're showing here. So draw it into a proper form with a bond line showing the shared pairs. Remember, for every bond line that you draw, you're representing a shared pair of electrons. Okay. Yes, like we do so far, yep. Hey, very good. Now, one last thing, one question. Why did you keep those couple paired of electrons on the oxygen? Why did you do that?
Like here?
Yeah.
Because they're with the oxygen and like.
Are they're not being shared?
Yeah.
Yeah. Good.
Yeah.
Okay, so that's good. Now, one last thing.
Okay.
Is this guy nonpolar covalent or polar covalent when it comes to its bonds? So you need some numbers, right?
Yeah.
Carbon has an Ion value of what, 2.55, right?
Yeah.
Oxygen is 3.44. So we want to know what the difference between those two might be. Covalent or polar covalent? Is it 0.5 or less?
It's greater.
It's greater than that, so it's got to be polar covalent. Yeah. PC. Good. Yes, well done. It's kind of hard to do this stuff. But you did fine. You did fine. And again, there's no harm in working through it. It works well for you. Okay, so if we're okay with all that stuff, then you'll get some practice with that in just a little bit. I do want to just move a couple things forward in our note outline, just so we're set up nicely for next week when we come back in. We dealt with that. I think we looked at ionic versus covalent, so we can actually get back to right here. I think we may have covered a little bit of this moving forward when we first introed this unit. But we should be very, very much aware that, obviously, basically with water, that it is a polar molecule, right? And polar is meaning that it has that slightly positive side, while you have a slightly negative side on the other side of the molecule, right? So we should already maybe sketch that into our notes, but if you haven't yet, here you go. And then oxygen is going to hog those electrons because it has a higher Ion value. We talked about that as well and looked at some examples of how that works. And then a positive charge on the hydrogen. And finally, we know that the water, when it's near another water molecule, the hydrogen atoms want to cozy up to the oxygen. Right? Now that cozying up is a special type of bonding known as hydrogen bonding. Right? And I'm just going to throw in the diagram here. All right, so we're not actually connecting these permanently. It just means that the positive charge on the hydrogen is drawn to the negative charge that we see show up on this polar molecule around the oxygen. Right? It's different than a chemical bond. All right. Yes, I know hydrogen is bonded to oxygen in the water molecule, right? But that's a chemical bond. It's a single chemical bond. We got that. But a temporary connection between one molecule to the next would be a hydrogen bond, right? And so this is where that water wants to kind of hang close to one another and kind of stick together in a certain way. Is that okay?
Yeah.
Okay. All right, we've talked about already, like if we slow these water molecules down, they're going to line up in a certain way, right? So we get that gapping of space between the water molecules, and that's what allows it to expand or causes it to expand when it freezes. So we've kind of dealt with that already. And then some water properties that we might want to mention here. And again, it has a high specific heat, meaning that it resists changes in temperature. It takes a lot of energy to move water from solid to liquid to gas state. And the reason is because we have a lot of those bonding ideas going on. It's a very strong polar molecule. They want to be held together and stick together because of hydrogen bonding and those charge differences, positive and negative sides of it. It wants to line up in a certain way. So that kind of holds those molecules together more tightly. And the more tightly the molecules are held together, the harder it is to move it from solid to liquid to gas. Because it takes more energy to separate them. it's nice because it helps us maintain a steady, constant body temperature. So when we're ill or something, we know that we want our body temperature increases. We metabolize a little more rapidly to up our body temperature, and we can kind of maintain that higher temperature until we make the conditions unwelcome for the bacteria or viral infection that we might be experiencing. It's cohesive. Water wants to stick to another water molecule, right? And so that kind of sets up surface tension. It allows you, because the water molecules like to be kind of lined up with one another, that meniscal layer that we look at when we measure things in graduated cylinders, that's due to not only cohesion, but we also have adhesion. It likes to stick to surfaces, right? And so when we put this water into like a graduated cylinder, we get a meniscus to it. So like the water striders or water insects can kind of hang out on the surface of the water because the cohesive properties of water, the water molecules want to stick together and stay near one another. So provided it's not too heavy, those hydrogen bonds can kind of hold the water together and not let the insect fall through the water, right? And then if we're looking at like measuring things out of a graduated cylinder, we measure from the bottom of the meniscus. And why do we have that meniscus? Because one, water's cohesive, it's drawn to itself, and two, it's adhesive, it wants to stick to the sides and climb up that column, that graduated cylinder. So they try to creep up the sides and also stick to one another, and so you get that dip for a polar molecule or polar substance in a graduated cylinder.